Hi, this is a video to show you how to use Salome to set up boundary condition patches and then import it into OpenFOAM and run your simulation. So first thing you need to do is go into a CAD package and save your geometry as a step file, which we can import into Salome. So I'm going to go to Geometry, and I'm going to go to File, Import, and find the step file. So it's my step file. It's been created in a millimeter unit environment, so OpenFOAM is working in meters. So you want to select yes here, or you'll scale your model by a factor of 1,000. So I can't see it now because it's very small, because this is working in millimeters. So fit all. So this is my geometry. So this is a casting mold. So this is copied from a paper just to see the mold filling. So it's quite a nice experiment to try with a simple shape. So what I want to do is make this the inlet patch, this the outlet, and I want all the rest to be wall. There's a couple of different ways to do this, but what I quite like to do is to make some surfaces in the geometry area before going to mesh. You can do it in mesh as well, but I think this is a bit easier. So what we're going to do is to create extract in the geometry module the patches we want, which we'll then use later on in the mesh module. So I'm going to go New Entity Group, Create, and I want to make it a surface, and I'm going to, that's the main shape, so that's that. I'm going to call it wall. And so you can select individual faces, but that can obviously be quite difficult sometimes, so I'm going to go select all. And then what I'm going to do is just remove the two faces which I don't want, rather than selecting all the ones I do want. So this is going to be my inlet. So you can see it's highlighted. That's what that face is. So I'm going to remove it. That's my outlet. Surface 113. I'm going to remove that. Then I'm going to go Apply and Close. So now I've got this surface wall here. I'm going to hide the mold. So you can see I've got just the outer surface. So now I'm going to do the same thing for the inlet and outlet. New Entity Group, Create, Surface, Main Shape, Full Mold. And I don't want to do Select All. So what I'm going to do is, what am I going to do? I've forgotten. That's right, I'm just going to click on the face. Add. So it's just my inlet, so I'm going to call that inlet. Apply and Close. I don't know why it does this. Sometimes it doesn't really do the renaming properly, so you need to watch out for that, because you could get really confused if you've got a lot of patches. I usually like to colour them. It's a bit annoying because you can't colour it when it's hidden, which is pretty stupid, so I've got to unhide it just to colour it. So this is making it now a bit more obvious what we're doing. And now I just need to make the outlet. So new entity group create face, and now it's forgotten where the shape is, so full mold, outlet, and then click, add, yeah, apply and close. Again, it's forgotten to rename it properly. Okay, so I'm going to colour that yellow. Okay, so you can see now what we've got. So I probably better save that. So now we're going to need to mesh it, so I'm going to go to Mesh Module. And it's really annoying because it hides everything, and yeah, so I'm going to have to unhide that. And it's also forgotten that I've zoomed in, so I'm going to have to zoom in again. And I'm going to expand that so I can see the walls I've created. Unhide them. The colours don't show up because I'm now in Mesh Module, so it's forgotten what I've done in geometry, but anyway. So the first thing I'm going to do is create the mesh for the main blob. So I'm going to go Mesh, Create Mesh. Geometry is going to be full mold because that's the solid piece. And I haven't got time to go into all the different kinds of mesh types you can use here, and to be honest I don't know all the details, so you have to make your own mind up about what's best for you, but I'm going to use NetGen. And you've got to put in a hypothesis, which is just to kind of tell it about the mesh size and all this kind of stuff, so you have to put something in there. Or if you want, you can do a kind of simple option, assign a set of hypotheses, which is kind of just going to do something automatically sensible, so it's easier, but you can't really control what's happening very well. So if you go here, I can then have a bit more options about what I'm going to do. So probably want fineness, so that's the overall size it's going to be, or the general idea for the size, and then you can put in minimum and maximum size, so that's looking not too bad there. Okay, so that's what I'm going to do for now. I'm not going to do any complicated options because the video will take too long. It's not the point of the video, so I'm just going to go OK, apply and close. So then it says mesh, and you can see there's a little very small warning triangle, which just means that you've told it what you want but it hasn't done anything. So you're going to right click and compute, which is actually going to make the mesh. So now it's going to tell you, it's going to bring up a window in a minute telling you how many nodes and elements it's created and if it's worked or not. There you go. So once you've done this a few times, it's good to make a note of this number here, number of nodes, because this is going to give you a pretty good rough estimate on your compute time. So it's handy to get a rough gauge for what's going on. But you won't know what this means until you've run a few simulations anyway. Okay, so that's basically how the mesh looks. So for my purposes that basically looks fine. There's nothing too weird there. I'm not going to go into the stuff you can look into to judge how good the mesh is, because again, that's not really what I'm supposed to do with this video, so that's going to have to be another one. So that's the mesh for the main bulk. So this is a solid mesh, 3D. So what I need to do now is make patches, mesh patches, which are 2D, which are going to be the walls. So inlet, outlet and wall patches. So again, I'm going to go mesh, and I'm going to go create group. So mesh 1, so that's the name of the mesh, and I want a face, and it's going to be wall, and I'm going to do group on geometry, and I'm going to need to expand this so I can get to these things here. Geometrical object and direct geometry selection, because I've already made the geometry. If you want to if you haven't done this, you'll have to use this one, and then you're going to be clicking on faces, and it's a bit of a pain, to be honest. So I'm going to do that, and then click wall. I find the interface isn't really very good, but sometimes it doesn't really select what you want, so it's good to constantly be checking that you've got the right names in here, because it's not really super user friendly. Okay, so I've got now a wall. So when I unhide this, you can see it says wall here. So all my mesh groups, it's going to put the name here. So again, you want to be checking. But annoyingly, it doesn't. If you've got it hidden here, it disappears here as well. So yeah. So I'm just going to do this exactly the same again for the inlet and outlet patch. Mesh, create group, select the mesh, mesh 1, name inlet, group on geometry, direct geometry selection, inlet. Choose color, red, apply and close. By default it's hidden, don't know why. So now it says inlet. I can't see it because it's probably hidden by all this other stuff, but I'll show you in a minute. Okay, so this is looking wrong, because this says groups of nodes, and I don't want nodes, I want a face, so I'm going to get rid of that. That's something, so I've done something wrong there. Yes, I want to delete it. So let's do that again. Oops. Create group. For some reason, I know I've gone create group and then done geometry, but for some reason, if you do this, it's not quite working in the same way, so I prefer to go into it through here. So that's probably what I did. I probably left that at element type node. That's why it didn't work last time. Forgot to select face. Mesh 1, name inlet, group on geometry, direct geometry selection. Oops, wrong. Inlet. Okay. Face, inlet, apply and close. Yeah. Okay. So you can see it now. So, and it's all under group of faces, which is correct. So I just got to make the outlet group. Mesh 1, face, group on geometry, direct selection, outlet, color yellow, unhide. So the colors don't matter at all. Like, this is not going to go into OpenFOAM, it's just for me to visualize what's happening with the patches. what is going to go into OpenFOAM are these names. So you better make sure you're quite comfortable with what you name these, because when you go into OpenFOAM you're going to need to modify some of your files to reflect these patch names. It's obviously case sensitive, so it's good to keep to a good regime of strictness about this. So I just call everything wall inlet outlet, all lowercase, just to so it's always easy. So basically this is now ready for export to OpenFOAM. So what I'm going to do is, in OpenFOAM I'm going to use import UNV. So I'm going to need to make a UNV output file. So I'm going to right click on mesh 1, not on mesh here, mesh 1. I'm going to go export UNV file. Then I'm going to save it. UNV tutorial, type UNV, save. So, yep, okay, that's fine. So we can get rid of this now. Maybe I'll just save it first. Quit, yep. So I'm just going to go and set up my OpenFOAM directory stuff now. So I'm going to go to OpenFOAM and then run, and this is a working one I've got already, but everything's already finished in here, so I'm going to make a new one and delete all the stuff so you can see properly that it actually works. And it's pretty ridiculously massive because this has got all the result files from the previous run, so that's why it's ridiculously big. Okay, so rename this. Tutorial. So this is the case directory. I'll explain a little bit of this because you might be watching the video and not really be an OpenFOAM expert, so probably useful to do that. So I'm going to delete all the rubbish I don't need. So the simple thing to say is that what I do need is system, constant, and 0. So I'm not going to delete those. And this is the old UNV mesh, so I don't need that either. Get rid of that. Processor 0 to 7, this is because I'm running this in parallel. So I've got 2 quad-core Xeons. So it's important to note when you're running this in parallel, it's on the number of compute nodes. It's not the number of physical CPUs. So I've got 2 physical CPUs, each with 4 nodes. So that's why there's 8 in total. So yep, I'm just going to delete all the stuff I don't want. Okay, this is not very pretty, but as you can see, I'm not really a Linux expert either. It's probably a smart way of deleting all these. So these are obviously all the results for each time step that I've chosen for the simulation. Don't want that either. Okay, good. So that's the basic structure of what I want. Now I'm going to put the UNV file I've just made. Oops, wrong one. In that directory. Okay. So I'm going to need to do some other stuff now. So Alpha1, so basically what I'm running here is basically a very modified case of the damBreak OpenFOAM case. So Alpha1 is the file which is basically defining the fluid volume that you're going to be, in this case basically you can consider it, this is defining the area of water within my box full of air that I'm going to pour in. And the way this works is that when I do my set fields, which you need to do to define your Alpha1 file, it's going to go and take all the info from set fields dict. Oops. So these are the two coordinates that define the volume of fluid that's going to drop, or whatever you want, into your box. So it's defined as XYZ min, XYZ max, which is the box to cell command. So it's not defining a box in the same way as you would in the main file to define the actual working area. So this is, just be aware, it's defined with XYZ min and point and one XYZ max point. So that's how it defines it. And basically it will draw this box, and wherever this box intersects with your main mesh, it will define this as being fluid. So it's only where this area intersects with your mesh that will become the fluid. So when I run set fields command, it's going to take this area here and it's going to take my Alpha1 file and it's going to put in a lot of stuff and and so when I was talking about making sure you've called your patch names in Salome something smart, it's because one of the things you'll have to do is make sure that your boundary conditions are named with the same exactly the same names that you've done in Salome, otherwise it won't work. So it's my wall, so it's 0 gradient. Inlet and outlet are inlet outlet because stuff has to go in and out of them, obviously. Yep. So what you need to be aware of is the reason this is called alpha1.org. .org doesn't mean anything, it's just a kind of a way of making sure it doesn't get used, because every time I run set fields it's going to overwrite this. So what you want, this is a backup, so every time you make a change to your geometry or whatever, you need to delete the old Alpha1, make a copy, paste it, rename it, and then get rid of the rubbish. So this is going to be my blank template, which will be filled in with values when I run set fields. So don't ever delete this or use your original one. PRGH, again your boundary conditions, and again you'll need to name these identically to your patches as you have done in Salome. So you've got to do that, and you've got to do the same thing here for your velocity. So boundary fields have to be named correctly. Yep. So that's all in the 0 directory. Polymesh, so this contains the old mesh that I imported, so I'm going to go in there and delete all the old stuff because I don't want that anymore. Another thing just to be aware of is if you go in your gravity folder, so this is basically XYZ, so just make sure that you've got your gravity running in the right direction, because sometimes when you're importing your geometry from your CAD package, you may find it's not facing in the same direction you had it when you created it, which doesn't matter. You can just put gravity to be any direction you want, but it's worth just checking. And transport properties, so in here I've just made some modifications to phase 1, which is the fluid volume, which for me has been defined by Alpha1, which is telling you where the phase 1 is going to be, and and phase 2 is the air, which is going to be the mesh area, which is not intersecting Alpha1. Yep. Turbulence properties I'm not using because I haven't set this to be a turbulent model, so that's not going to do anything. So this is the most important one, which is going to define the simulation. Decompose Predict. I'm going to look at this briefly because I'm going to run this in parallel, and if you don't have this set up correctly, you will not be able to run it in parallel. So number of subdomains, that's the number of the nodes, compute nodes I have, which is 8. And basically, roughly speaking, what I'm saying here is that this is going to divide the compute domain into 8 blocks. So obviously if you've got a cube, which each face of which has been subdivided twice, you're going to end up with a cube formed of 8 smaller cubes. So the reason I've done that is because I've got 8 cores. So that's an example of how you can set it up. Set fields dict, again, just to go over that once more. This box to cell is the coordinates x, y, z in meters, min, max. That is going to define Alpha1, which is your phase 1, which is for me the fluid volume. So if you've not set this up correctly, it won't work. These two I haven't touched. So, oops. Just look at the control dict. So that's my time step, write interval, so it's computing all of these, but it's only actually going to write the results down for each 0.025 seconds. And this is some stuff when you're working with the multi-phase. So max alpha, so this is controlling the phase interface accuracy. So if you're having some problems getting the simulation to run, reducing this number is one thing you can do, along with reducing the delta t to get the courant number down to hopefully make it run properly or run at all. And having adjustable runtime is a good idea generally as well. Anyway, so I've now purged this of all the old stuff and I put the new UNV Mesh in there. So let's import the UNV Mesh and set it up to run. So I'm running CAE Linux. So to start OpenFOAM, I'm just going to click here. So I'm just going to navigate to this directory now. So I'm just going to put a few basic tips in here because, as I say, not everyone's going to be au fait with Linux. So if I put in most of the name and then press tab, it's going to fill in the rest of it for me, which is going to be quite useful later on. ls is going to show me what's in the directory. So that's good. I can see the UNV is there and all the other stuff, so that's fine. So what we're going to do now is import the UNV Mesh into OpenFOAM, and that's going to import our patches as well. So we're going to go ideas, press tab, or put in the rest of the command. Ideas UNV to foam, so it's going to obviously convert the UNV to foam, and then you just need to put in the name of this, so you just put in the first couple of letters, tab, enter. So important things to look at here. Do I have any unpleasant sounding errors? Nope. It says end, that's good. And what's very important to note, wall inlet outlet. Okay, so you can see it's correctly imported our 3 patches. And again, just make a note again of your syntax here, just to really make sure that it's going to work. Because even if you've got 1 capital letter in there, it won't work. So I've now imported that. So if you go into constant polymesh, you can see it's, so this is your mesh data. Now what I'm going to need to do is create my Alpha1 information, which is going to define the fluid, the phase 1 volume. So again, wall inlet outlet, copy my patch names. But when I run set fields command, it's going to overwrite this. Okay, so this is because I'm running multi-phase simulation. So if you're running some one of the other solver types, you won't, this particular command you might not be doing. So again, that looks happy, and yeah, it's done something. We've got some values, so that's fine. That's good. The next thing we probably should do is just check the mesh to see if it's reasonably happy. So check mesh, all okay, mesh okay. Yeah, I'm not going to get into looking at all these different informations, but basically there's a good start that it's probably going to, maybe going to work. Now normally I would just run the simulation at this point, but because I'm going to run this in parallel mode, I need to decompose the simulation into 8 different subdomains, and when I run this command, it's going to take the information from we put in the decomposed pardict. So it's going to put in, so it's going to go into here and say, okay, I want 8 subdomains, and yeah, all this stuff. So that's why you need to edit that. So decompose par, return processor 0 to 7. Let's just check processor 0 to 7. Okay, good. And at this point, what's a really good idea, especially with the multi-phase, is to have a look at the mesh and check that actually the area we've defined as the Alpha1 zone actually intersects where we hoped it was going to intersect with the main mesh, because when you're just working in text file XYZ coordinates, it can get a bit messy. So let's just go into parafoam, paraview, but the command's parafoam. So there's obviously no results available, but we can look at what we have. So that's very good. So that's the right shape. So I'm going to select Alpha1. There's no point selecting velocity because we haven't run it. There are no velocity data available. But Alpha1 is available because that's something we've already computed. So I'm going to go up here to Alpha1. And if you want, you can go wireframe. So then we can look at the mesh, and the red area is basically saying, so this is the area where Alpha1 is. So this is going to be the red bit's going to be the fluid volume at the start. So basically that all looks pretty good. And you can see here it says Z. And I don't know if you can remember when we went to the G file, I had Z set to -9.81. So this is when you want to be checking that you don't have your G set to Y or X. Well, it depends on what orientation you want, but up and down is this way for me, so just check that. Okay, so let's get rid of that. So that's all looking pretty good. We've run set fields and we've run decompose pass, so now we can actually run it in parallel. And I'm not going to run the whole thing because it takes about 18 hours. I've got 5 seconds of stuff to do. So what I'm going to do is just do a fudge here. Oops. And I'm not going to say end time is 5 seconds. I'm going to say it's 0.1. 0.1. That'll do. Just put a little note in there so I remember what I've done. Okay, so I'm going to cheat a bit here because I've already typed in this command previously, but you can see. So it's multiprocessor run, np, number of processors, space 8, interfoam, name of the solver, minus parallel. So you want to check you have correct number and then run. And now we're making some results. Wondering how long this is going to take to get to 0.1. Probably a couple of minutes actually. So I don't think I have anything intelligent to say for the next 5 minutes, so I'm probably going to cut some stuff out of the video when I actually put it online. Okay, so we're 1/10 of the way there, so yeah, it's going to take a couple of minutes. Just see if I can think of something interesting to do in the meantime. So if you want to check how it's going, you can go into one of your processor directories, and in a minute the results at whatever time step you've specified are going to start appearing in here in folders. So the next one should be 0.025, and that'll continue up to 0.1 because that's the end time. What else is interesting? Not a lot. So we're just waiting for this to happen now, basically. 0.03. Oh, what am I talking about? There is interesting things going on. So courant number max. So right now we're about 0.3, and the basic guideline for most things is that if it's above 0.5, that's probably not really good, and if it's above 0.7, that's definitely very bad. And if your courant number maximum is kind of 0.7 or above, probably what you want to do is not even bother waiting for the thing to get any further. It's just quit out and go and decrease your time step, because it's basically not going to work. Or the result's going to be so meaningless that there's no point even looking at it. So that's kind of worth paying attention to when this is all happening. What are we up to now? 0.05, so we should have yeah, got another file appearing here. So there are some other tricks you can do to actually get your patch names correctly into OpenFOAM. So for example, one thing you can do is to, depending on your geometry, you can actually use an automatic function whereby you can just define your inlet and outlet patch, and then you can basically just tell OpenFOAM that's to automatically call everything you haven't named the wall, given an angle change between elements. So that would basically work if you've got a sort of an organic shape with a couple of sharp edges for the inlet and outlet, and then it can actually automatically select all the other stuff for you. But I prefer just to do it all in Salome. I'm sure there's lots of other possibilities for doing it, but I've never used them, so I can't tell you anything about them. Where are we? Point 8, just about there. Probably won't be able to see very much when it's run, but at least I can prove that this has actually worked, which is the point of the exercise. So I've been using OpenFOAM for about 8 months, on and off. It's not my job, so it's just in my spare time, the occasional weekend or evening, so by no means any kind of expert on it, but getting there very slowly. So I learned a lot of this stuff a few months ago, actually, at University of Genoa in Italy, and there's a guy called Joel there who is running a very good OpenFOAM course which lasts 5 days, and I think he might be running more than one a year, but I'm not sure, so actually I can show you. I'm going to slow this down a bit. Yeah, so this is the one I went to, which lasts for a week, and I really recommend it very heartily, because if you haven't used OpenFOAM before, if you go to one of these ones that's 1, 2, or to be honest even 3 days long, unless you've got previous experience with CFD programs, you're not going to get there, honestly. So I think a week, honestly, it's really good if you don't have background, or even a little bit. So you can, this is his company here, Wolf Dynamics, so to which I'm not affiliated at all, I just enjoyed it. I've also been to a course at Technical University Delft for 1 day, which is also nice, but in 1 day, honestly, you've got no chance. Okay, so it's working. Now, normally we could just go to ParaView and look at the results, but we've run this in parallel, so we're going to have to put all the 8 subdomains back together again before you view the result. If you don't do this, basically it's really annoying, because you'll go into ParaView and you'll run it and nothing happens, and you'll get very annoyed, and then you'll realise you've been an idiot and forgotten to put domains back together. Oops. Reconstruct par, so I'm going to have to do this. So it's going to do this step for each time step, and that seems to have worked. So now we can go to ParaFOAM and check out if it worked. Okay. So what I'm interested in is Alpha1, so that's our fluid volume, and I'm going to go to Alpha1 here. Okay, so you can see that's looking like we want, and I'm going to go to threshold, and just to find Alpha1, and I'm going to put in lower threshold something, so that's going to hide, basically effectively going to hide everything that's not Alpha1, but I'd quite like to see the mesh as well, so I'm going to unhide that. But I want to see inside, so I'm going to say wireframe. So this is quite a nice way of visualizing the multi-phase, because you can kind of see the boundary but also see the stuff going on as well. Then I'm just going to play it, which is not going to be very interesting because we've only got 4 time results, but yeah, so it works basically. What I'll do is I'll just briefly show you the full simulation because it looks a bit more interesting, and it's a bit lame just kind of showing that. So that was casting 4, so oops, oh, I'm lost. Where am I? Okay. Okay, very good. So this is already complete, so I'm just going to go to Alpha1. Okay, so this is exactly the same, it's just got 5 seconds of data, so it's just a bit more fun to watch. Alpha1 threshold, small number, unhide, wireframe, and then go. So that's, yeah, it's a bit more interesting than the last one. So ideally what I really need to do is to raise my Alpha1 a bit, because A, I don't have enough fluid to fill up the volume, and also when it's kind of getting a low level like this, there's a lot of air entrainment happening, which is not really very representative, but this is a problem with my boundary setup, not anything else. But anyway, it's pretty cool. So anyway, I hope now you will be able to use Salome to create boundary conditions and put them into OpenFOAM and use it to run simulations with real world geometry you've created from a CAD program, which, if you're just getting into OpenFOAM, is not at all straightforward. So I hope you found this very useful. I don't have a huge amount of knowledge about OpenFOAM other than this, to be quite honest, but if you have any particular requests to make a video, I'll quite happily think about it, and we'll see. Anyway, so please just send me an email through my website or put a comment to let me know what you think, and I hope you can use the video to make fun stuff in OpenFOAM. Thanks very much.